December 27th, 1940. A conference room in New York City. Henry J. Kaiser, a 58-year-old construction magnate who had never built a ship in his life, signed a contract with the United States Maritime Commission promising to deliver 30 cargo vessels within 2 years. Across the table sat representatives from Todd Shipyards and Bath Iron Works, America's most established maritime builders, who had reluctantly agreed to partner with this outsider. Kaiser's chief engineer, Bedford, sat beside him reviewing technical specifications. Bedford had spent the previous month touring Ford Motor Company's Detroit assembly plants, watching automobile chassis move down production lines with workers installing prefabricated components at precise intervals. He returned to California convinced that ships could be built the same way. The maritime engineers in the room considered this comparison absurd. What none of them knew was that Kaiser had already made a decision that would horrify the entire shipbuilding establishment. He would eliminate riveting entirely. Every ship built since the Age of Iron had been joined together with heated metal pins hammered through overlapping steel plates. 1 million rivets per vessel, thousands of hours of skilled labor, 300 tons of dead weight added to each hull. Kaiser proposed using electric arc welding instead. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The British Royal Navy had explicitly forbidden welding on warship hulls. The United States Navy used it sparingly, only for non-structural elements. Every maritime architect trained in the previous half-century had learned that riveted joints were the foundation of reliable ship construction. The reliability of rivets was a matter of historical record. Welding was an unproven technology that locked mysterious stresses into steel, stresses that no one fully understood. Yet here sat Kaiser, proposing to bet America's supply lines on a technique he had learned building pipelines across the western deserts. Vice Admiral Emery Land, chairman of the United States Maritime Commission, examined Kaiser's proposal with the deep skepticism of a career naval architect. Land had spent decades designing submarines and overseeing ship construction. His private correspondence, now preserved in the National Archives, revealed his profound concerns about welding technology applied at scale to merchant vessels. Welding has never been proven reliable for hull construction at this magnitude. The British Navy explicitly prohibits welding on warship hulls for sound engineering reasons. Kaiser is proposing we wager America's ability to supply our allies on an unproven industrial technique. But Land also recognized desperation. By late 1940, German U-boats were sinking Allied merchant ships faster than British yards could replace them. The mathematics were brutal. Britain needed hundreds of cargo vessels immediately. Traditional American shipyards, using conventional riveted construction, required an average of 230 days to complete a single merchant ship. At that pace, the Allies would lose the Battle of the Atlantic before American industrial capacity could respond. The German submarine campaign was achieving its strategic objective. In 1941 alone, approximately 3.6 million tons of Allied shipping would disappear beneath the waves. Britain was literally starving. Its imports had fallen by a third. Food rationing grew more severe each month. The island nation could not survive without a massive influx of American supplies delivered by ships that did not yet exist. Land's approval of Kaiser's contract represented not confidence but necessity. Someone had to try something different, even if that something violated every principle of maritime engineering established over the previous century. The decision to use welding rather than rivets would accelerate or doom the Allied war effort. No one knew which. The technical objections to welding were substantial and well-founded. Traditional riveting created joints where individual steel plates remained mechanically distinct. Each plate could expand and contract with temperature changes. Each rivet allowed tiny amounts of flex. If a crack developed in one plate, it would stop at the riveted seam. The next plate was a separate piece of metal. The crack could not propagate. Welding eliminated these natural barriers. When an electric arc melted two steel plates together, they became a single, continuous piece of metal. Any crack that started could race through the entire structure at terrifying speed. The welding process itself introduced additional problems. The intense heat altered the steel's molecular structure in unpredictable ways. As welds cooled, the metal contracted, pulling and warping plates, locking internal stresses into the structure. Traditional shipwrights understood rivets through generations of experience. They knew how rivets behaved in storms, in collisions, in combat damage. They could calculate rivet strength with confidence. Welding was different. Welding was new. The locked-in stresses were invisible. The long-term behavior of welded hulls in harsh ocean conditions remained unknown. William Francis Gibbs, America's most respected naval architect, had designed more ships than Kaiser had probably seen. His firm, Gibbs & Cox, had created the Liberty ship plans by adapting British designs for American construction. Gibbs watched Kaiser's ambitious timeline with professional skepticism. He had devoted his life to understanding how ships behaved in the ocean's relentless environment. Kaiser had devoted his life to moving dirt and pouring concrete. The gulf between their expertise seemed unbridgeable, yet Gibbs also recognized that conventional wisdom might be wrong. The Liberty ship design his firm had created already incorporated some welding in non-critical areas. German shipbuilders had used welding on their pocket battleships in the 1930s to reduce weight and squeeze more firepower within Treaty of Versailles restrictions. The Soviet Union had built welded merchant ships. The technology existed. What remained uncertain was whether it could be implemented rapidly by inexperienced workers building ships at unprecedented speed. Kaiser's Richmond shipyard rose from empty mudflats between January and December 1941. His construction crews, experienced in building dams and highways but ignorant of maritime traditions, erected a facility that horrified traditional naval engineers when they visited for inspections. Instead of the massive gantry cranes and longitudinal building ways that characterized established shipyards for centuries, Richmond featured something entirely different. The yard was laid out like an automobile assembly plant. Open areas for prefabrication surrounded 7 parallel building ways. Railroad tracks crisscrossed the facility, designed to move massive steel sections weighing up to 150 tons. Overhead cranes capable of lifting entire ship sections stood every 100 feet. John Riley, chief naval architect for Bethlehem Steel Corporation and a 30-year veteran of ship construction, visited the Richmond Yard in May 1941. His inspection report, marked confidential at the time, contained both technical criticism and grudging admiration. Kaiser has violated every principle of efficient shipyard layout I learned in 3 decades of professional experience. His prefabrication areas are too large. His crane capacity is absurdly excessive for any rational construction sequence. His building ways are too short for proper hull construction. Yet I must admit the facility is designed for exactly what he claims to achieve: rapid assembly of prefabricated sections welded together. Whether this approach will produce seaworthy vessels remains an open question. The arrival of workers provided the next phase of the revolutionary change. Traditional shipyards recruited from established maritime communities where skills passed from father to son across generations. These were craftsmen who understood ships in their bones, who could read blueprints and improvise solutions based on years of experience. Kaiser advertised in newspapers across America, offering wages 20% above standard industrial rates and promising to train anyone willing to work. The first groups arrived in Richmond in August 1941. Former secretaries, farmers, housewives, laborers from closed factories, people who had never seen the ocean, much less built vessels designed to cross it. The maritime establishment predicted disaster. How could untrained workers possibly build complex ships? Traditional welders spent 4 years as apprentices learning comprehensive skills. They needed to understand metallurgy, recognize different steel grades, adjust technique for varying plate thickness, read structural drawings, and anticipate how their work would behave under the stresses of ocean travel. Kaiser's instructors taught specific techniques for specific tasks in approximately 2 weeks. Workers did not need to know how to weld everything. They only needed to know how to weld vertical seams on bulkheads, or horizontal deck plates, or curved hull sections. Tasks they would repeat hundreds of times. The simplification of complex skills into repeated simple operations borrowed directly from assembly line manufacturing. The approach proved devastatingly effective. By October 1941, Kaiser employed over 10,000 workers in Richmond. Fewer than 200 had any previous maritime experience. The yard was producing ships anyway. Clay Bedford's visit to Ford's Detroit assembly line had revealed the key insight. Modern manufacturing succeeded not through universal craftsmen, but through task specialization. Each worker performed one operation repeatedly until they achieved extraordinary speed and precision at that single task. The final product's quality depended on proper coordination of specialized workers, not on individual workers possessing comprehensive knowledge. Applying this principle to shipbuilding required rethinking the entire construction process. Traditional shipyards built vessels sequentially, from keel to deck, hundreds of workers crowded together around a single hull, each waiting for previous steps to complete before beginning their own work. Kaiser's prefabrication approach built entire sections simultaneously across the facility. While workers in one area fabricated the bow section, teams elsewhere assembled the stern, the midship structures, deck houses, engine mounts. Each section took shape on its own assembly platform, where it could be built in the most efficient position, often upside down or on its side to make welding easier and therefore stronger. When sections were complete, massive cranes lifted them onto the building ways where they were welded together into a complete hull. The first Liberty ship Kaiser's Richmond yard produced took 197 days from keel laying to delivery. Maritime experts considered this respectable for a new yard using an untried workforce. Ship number 2 required 169 days. Ship number 5 took 128 days. Ship number 10 took 97 days. By spring 1942, Richmond was completing Liberty ships in 70 days on average. Traditional shipyards watched with growing alarm as this untrained workforce achieved production speeds that matched their own highly skilled crews. The welding approach that traditional builders had dismissed as dangerous and impractical was working. Each completed ship was 441 feet long, 57 feet wide, with 5 cargo holds capable of carrying 10,000 tons of war materials. The vessels used a simple triple expansion reciprocating steam engine, an outdated design but one that multiple manufacturers could produce quickly. Top speed was 11 knots, barely faster than a brisk walk. The ships were ugly, utilitarian, designed for a single Atlantic crossing if necessary, but they floated, they sailed, and most importantly, they kept appearing from Kaiser's yards at accelerating rates. The prefabrication approach revealed its power through autumn 1942. Instead of building ships from keel to deck in sequence, Kaiser's yards fabricated sections simultaneously. A ship's construction time was no longer determined by how long it took to complete each sequential step, but by how long it took to build the largest single section. Entire deck houses were assembled in dedicated fabrication areas, where these pieces could be built on their sides or upside down, making the welding easier and therefore stronger. Engine foundations were prefabricated as complete units ready for engines to be dropped in. Bow sections took shape as single massive assemblies. When the time came for final assembly, cranes lifted these sections onto the building ways, where they were welded together in days rather than months. The transformation of construction time was remarkable. Traditional shipyards had assumed certain steps required certain durations based on decades of experience. Kaiser questioned every assumption. If a task took a week using conventional methods, could prefabrication reduce it to days? If hull plates were traditionally installed one at a time, could entire plate sections be assembled as units? The answers were usually yes. Almost everything could be done faster if you abandoned tradition and focused only on results. By November 1942, Kaiser's confidence in his system had grown absolute. He announced that Richmond Yard No. 2 would attempt something unprecedented, building a complete Liberty ship in less than 5 days. The maritime establishment considered this claim impossible. Building a ship required time for steel to be aligned, for welds to be inspected, for systems to be tested. You could not simply weld a ship together in days and expect it to survive ocean conditions. Kaiser believed otherwise. November 8, 1942, a Sunday morning. The keel plates for a new Liberty ship designated SS Robert E. Peary were laid at Richmond Yard No. 2. Newspaper reporters and competing shipyard owners gathered to witness what Kaiser claimed would be possible. A complete cargo vessel, 441 feet long and capable of carrying 10,000 tons, built in less than 5 days. Traditional shipbuilders came to watch Kaiser fail. They brought stopwatches and notebooks, ready to document the chaos they expected when untrained workers tried to assemble a ship at impossible speed. What they witnessed instead was a choreographed industrial ballet that operated 24 hours a day without pause. Prefabricated sections arrived at the building way in carefully planned sequence. The moment one section was lifted into position and tack welded, the next section was already moving into place. Welding crews worked in shifts, never allowing the arc to go cold. Inspection teams followed minutes behind the welders, checking seams while they were still hot. The bow section, built over the previous 2 weeks in the prefabrication area, was lifted onto the keel on the first day. The stern frame followed 6 hours later. By day 2, the bottom plates were complete. By day 3, the hull sides were rising. By day 4, the deck sections were being lowered into place. Thursday, November 12th. 4 days, 15 hours, and 29 minutes after the keel was laid, the SS Robert E. Peary slid down the building way into San Francisco Bay. A complete Liberty ship, faster than anyone in maritime history had thought possible. The crowd erupted. Journalists rushed to file stories. Newsreel cameras captured the moment. Kaiser had not just met his bold prediction, he had demolished it. The Robert E. Peary represented more than a construction record. It represented proof that industrial revolutions could happen in months rather than decades when necessity and innovation combined. Vice Admiral Land sent a terse telegram. Congratulations on achievement that would have seemed impossible 2 years ago. The British Merchant Shipping Mission sent more effusive praise. Britain was surviving on American cargo deliveries. Every ship built meant more food for civilians, more ammunition for soldiers, more fuel for aircraft. The speed of Liberty ship production was literally determining whether Britain could continue fighting. By early 1943, American shipyards using Kaiser's techniques were launching 3 Liberty ships per day. The mathematics of attrition had reversed. German U-boats were still sinking Allied ships, but American yards were now producing vessels faster than submarines could destroy them. The tonnage war Hitler had counted on winning was being lost in the shipyards of Richmond, Portland, and Baltimore. Then the ships started breaking. January 16, 1943, Portland, Oregon. The SS Schenectady sat quietly at dock. She was a T2 tanker, built using identical welding methods as Liberty ships, 10 weeks old, fresh from Kaiser's Oregon yard. No enemy action threatened her. No storm battered her hull. The morning was calm, the water still. Without warning, a sharp crack echoed across the harbour. Within moments, the entire vessel fractured completely in two, the hull splitting from deck to keel as if sliced by an invisible blade. Sailors scrambled as the bow and stern sections sagged in opposite directions, the ship's back broken while tied safely to the pier. The Schenectady was not alone. That same winter, the SS John P. Gaines broke apart in calm seas. The SS SO Manhattan cracked so severely her crew abandoned ship in panic. Between 1943 and 1944, more than 200 Liberty ships reported serious structural failures. Hull cracks, deck fractures, catastrophic splits. At least 19 vessels broke completely in half. 3 simply vanished at sea, disintegrating so rapidly they could not even send distress signals. These were not war casualties. These were ships committing suicide. The Maritime Commission convened emergency investigations. Metallurgists examined failed sections under microscopes. Engineers reviewed stress calculations. Naval inspectors crawled through hulls with measuring instruments. Everyone searched for the culprit. Bad steel, faulty welds, design flaws, inadequate quality control. Ships continued splitting while committees debated. The cracks typically started at sharp corners. Hatch openings, gun mounts, the squared-off design of the hull. Once a crack initiated, it propagated through the welded hull plates at terrifying speed, sometimes racing the entire length of a ship in seconds. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The traditional maritime engineers who had warned against welding felt vindicated. They had predicted this. Welded hulls lacked the natural crack-stopping barriers that riveted construction provided. Kaiser faced a brutal calculation. The Liberty Ship program was already under congressional scrutiny. Senator Harry Truman's special committee to investigate the National Defense Program was examining cost overruns and quality problems across war production. Liberty Ship failures were becoming a scandal. Newspaper editorials questioned whether Kaiser's speed had come at the expense of seaworthiness. Sailors grew terrified of their own vessels, knowing the hull beneath their feet might unzip without warning in cold Atlantic waters. The maritime establishment that had reluctantly accepted welding now demanded a return to proven riveted construction. Vice Admiral Land faced political pressure to cancel Kaiser's contracts and shift production back to traditional shipyards using conventional techniques. But Land also understood the mathematics. German U-boats were still sinking Allied ships daily. Switching back to riveted construction would cut production rates by more than half. The time required to retrain workers, retool facilities, and redesign construction sequences would create a months-long gap in ship deliveries. Britain might not survive that gap. Land needed answers. He needed them fast. And the answers were not coming from the engineers and metallurgists who had spent months analyzing failed ships without reaching definitive conclusions. The breakthrough came from the least likely source. Not from the engineering departments, not from the naval architects, not from the metallurgical laboratories, but from the welders themselves, the workers who actually touched the steel every day, who felt how the metal moved under their torches, who watched plates warp as welds cooled. Bessie Hamill worked the graveyard shift at Kaiser's Richmond Yard No. 3, one of thousands of women who had flooded into shipyard work after men shipped overseas. She had been welding hull sections for 8 months, long enough to notice something the engineers apparently had not. Every night she watched her team weld massive steel plates in a sequence that made no mechanical sense whatsoever. Welders started at the edges of plates and worked inward, or they began at one end of a long seam and ran straight to the other end. As each weld cooled, the metal contracted, pulling and warping the plates. She could see the stress building. Watch the steel distorting under her torch. When welders finished one section and moved to the next, they were effectively locking that stress into the structure permanently. It was like tightening the center bolts on a car wheel before securing the outer ones, a recipe for imbalance and failure. Her foreman dismissed her concerns. She was a welder, not an engineer. The sequence came from the engineering department, from men with college degrees and naval architecture training. What could a night shift worker possibly know that trained engineers had missed? Hamill persisted anyway. In November 1943, she requested a meeting with yard supervisors, breaking chain of command protocol that could have gotten her fired. She brought samples, test plates she had welded on her own time using different sequences. Some showed significant warping and visible stress patterns. Others, welded from the center outward in a carefully planned sequence, lay flat and true with minimal distortion. The supervisors were skeptical but intrigued. One agreed to observe the production line during Hamill's shift. What he saw confirmed her observations. Welders were essentially torturing the steel, forcing it to accept stresses it would carry for its entire service life. Every cooling weld created residual tension in the metal. The construction sequence meant these internal stresses accumulated and concentrated at specific points, particularly at the corners of hatch openings and other stress concentration points. When those ships hit cold North Atlantic water, the steel became brittle. The locked-in residual stress combined with brittleness created perfect conditions for catastrophic fracture. Hamill's insight was elegantly simple. Weld from the center of sections outward, allowing stress to dissipate toward the edges rather than concentrate in the middle. Alternate welding locations to prevent heat buildup in any single area. Never complete welds in long continuous runs. Instead, use a balanced sequence that distributed cooling stresses evenly. These were not revolutionary metallurgical theories. They were practical observations from someone who actually worked with the material every day, who felt the metal move under her torch and recognized the consequences. By December 1943, her observations reached Henry Kaiser himself. He faced a decision that would define his legacy. He could acknowledge that the construction sequence, not the steel quality or weld integrity, was the fundamental problem. That would mean admitting that every ship built so far had systematic flaws baked into their hulls. It meant temporarily slowing production to retrain thousands of welders. It meant redesigning the entire assembly process. Or he could dismiss a night shift welder's observations and continue building ships the way his engineers had designed. Kaiser, to his credit, did not hesitate. He authorized immediate testing of Hamel's theories, pulling an entire hull section from the production line for experimental reconstruction. The metallurgists and engineers who had spent months analyzing failed ships were now taking instruction from a woman who had never seen the inside of a college classroom. The test results were damning and revelatory in equal measure. When Kaiser's metallurgists examined hull sections constructed using conventional sequences versus Hamel's methods, the difference was measurable and dramatic. Residual stress gauges showed traditional welds carried internal tensions exceeding 30,000 pounds per square inch, concentrated at key structural points. Hamel's center-outward sequences reduced residual stress by more than 60%. The implications were immediate and expensive. Every ship under construction needed revised welding procedures. Every welder needed retraining. The production speed that had made Kaiser famous would slow while new methods were implemented and perfected. But the alternative was continued catastrophic failures, continued deaths of merchant mariners, continued loss of desperately needed cargo. Kaiser made the only decision that mattered. He halted production for retraining. In January 1944, Kaiser's yards implemented new welding protocols across all facilities. Welders learned to work from section centers outward. Supervisors monitored heat patterns to ensure no single area accumulated excessive thermal stress. Inspection procedures were revised to check not just weld quality but welding sequence compliance. The changes worked. Ships built using the revised procedures showed dramatically reduced cracking. The catastrophic failures that had plagued the program through 1943 began declining. By mid-1944, new construction Liberty ships were completing their Atlantic crossings without structural issues. The crisis had revealed a profound truth about industrial innovation. Speed alone was not enough. Kaiser's revolutionary production techniques had achieved unprecedented construction rates, but those rates meant nothing if the ships broke apart before delivering their cargo. The real achievement was not the 4-day construction of the Robert E. Peary. The real achievement was recognizing when speed had to be sacrificed for correctness, having the courage to halt production and redesign processes based on a welder's insight that contradicted established practice. That willingness to listen to frontline workers, to admit that engineering theory had missed something crucial, to redesign systems around observed reality rather than defend assumptions. That was the actual revolution. The lessons learned from Liberty ship welding failures transformed not just shipbuilding, but industrial manufacturing across every sector. The American Welding Society, founded in 1919, published its first comprehensive structural welding code in 1947. That code codified center-outward welding sequences and stress relief requirements as mandatory standards. Every welded structure built since, from skyscrapers to pipelines to pressure vessels, follows procedures descended directly from the methods developed at Richmond Shipyard in 1944. Pipeline construction across Alaska in the 1970s relied on welding procedures that explicitly referenced Liberty ship and Victory ship methods to prevent cold weather cracking in Arctic conditions. The Trans-Alaska Pipeline, 800 miles of welded steel carrying hot oil through sub-zero temperatures, exists because engineers understood the lessons Bessie Hamel taught. Modern bridge construction inherited the same principles. The catastrophic failure of the Silver Bridge spanning the Ohio River in December 1967, which killed 46 people, included residual welding stress as a contributing factor. The investigation revealed welds executed without proper sequencing had locked stress concentrations into structural members. Post-disaster code revisions mandated the sequencing and inspection protocols Liberty ships had pioneered. Every welded bridge built since incorporates those requirements. The offshore oil industry learned the lesson repeatedly, always at terrible cost. The Alexander Kielland platform disaster in Norway in 1980, where 123 workers died when the platform capsized, traced partially to fatigue cracks propagating from improperly sequenced welds. The Piper Alpha platform explosion in 1988, killing 167 men, began with a crack in a welded pipe connection that had accumulated residual stress. Each disaster prompted investigators to examine welding procedures. Each investigation rediscovered principles that Liberty ship construction had proven 40 years earlier. Nuclear pressure vessels containing reactor cores under extreme temperatures and pressures represent the ultimate application of stress relief welding. The massive steel shells enclosing nuclear reactions cannot tolerate any crack initiation points. Welding sequences for reactor vessels are planned with computational precision, simulating thermal effects and residual stresses before the first weld is struck. The entire vessel receives post-weld heat treatment in enormous ovens, exactly as Victory ship sections did, eliminating residual stresses that could become failure initiation points. The engineers designing these procedures in the 1950s explicitly studied Liberty ship construction as their foundational reference. Hamill's observation fundamentally altered how engineers think about fabrication processes. Before Liberty ships, design and construction were separate domains. Engineers designed structures, fabricators built them. The two groups rarely communicated about how construction methods affected structural performance. Liberty ships proved that fabrication sequence was as critical as material selection or structural design. Modern engineering education now includes manufacturing processes as integral components of design courses. Engineering students learn that a perfect design executed with poor fabrication sequence produces inferior results compared to a modest design built with proper procedures. The 5-day construction timeline of the Robert E. Peary, while impressive, was never the real achievement. Kaiser's yards could have maintained that speed indefinitely, launching defective vessels that looked seaworthy until they fractured. The actual miracle was slowing down enough to do it right, having the courage to halt production and redesign processes when frontline workers identified problems that educated engineers had missed. That willingness represents the true revolution Kaiser brought to American industry. Not just speed, not just prefabrication, not just welding instead of rivets, but the organizational principle that workers observing the process often see what engineers calculating from desks cannot. Every modern manufacturing methodology, from Six Sigma to lean production to total quality management, embeds that principle. The person doing the work often knows more about improving the work than the person who designed it. By the war's end in September 1945, American shipyards had built 2,710 Liberty ships and 531 Victory ships, an improved design incorporating the welding, lessons learned through painful experience. Those ships carried 11 million troops overseas. They delivered 21 million tons of supplies to Allied forces. They made possible the invasions of North Africa, Sicily, Italy, and Normandy. Admiral Chester Nimitz, commander of the Pacific Fleet, reflected on the strategic impact of American maritime production in his post-war memoir published in 1960. We fought across 5,000 miles of Pacific Ocean, supplied by ships built faster than the enemy could sink them. Japan's military planners assumed American industrial capacity was impressive but finite. They believed that if they sank enough ships, eventually American logistics would collapse, and we would be forced to negotiate. They failed to account for Henry Kaiser and the industrial revolution he brought to shipbuilding. By 1944, we were replacing shipping losses faster than they could inflict them. The mathematics of attrition favored the side that could build 3 ships daily over the side that could sink 2 ships daily. Industrial capacity, not martial valor, determined the outcome. Vice Admiral Emery Land, who had been so skeptical of Kaiser's welding proposal in December 1940, spent the post-war years defending the Liberty ship program against critics who focused on the failures while ignoring the larger success. In testimony before Congress in 1947, Land stated plainly, "We took calculated risks with welding technology because the alternative was certain defeat. Yes, ships failed. Yes, men died. But far more men would have died if we had not taken those risks." The ships that succeeded delivered the materials that won the war. Industrial warfare requires industrial courage, the willingness to try unproven methods when proven methods are insufficient. The program demonstrated that perceived limitations on industrial capacity often reflect organizational and conceptual constraints rather than physical impossibilities. Before Kaiser, manufacturing executives accepted conventional wisdom about production limits, skill requirements, and organizational structures. Kaiser demonstrated that conventional wisdom could be questioned, that breakthrough performance required challenging fundamental assumptions. That lesson proved as significant as the physical ships produced. It changed how American industry thought about what was possible. It changed how engineers approached design challenges. It changed how managers organized production. It changed how workers understood their role in identifying and solving problems. Bessie Hamill returned to civilian life in 1946 without fanfare or recognition beyond her shipyard supervisor's commendation letter. She never received a medal, never testified before Congress, never saw her name in the technical papers that later documented the welding revolution she had sparked. The engineering establishment absorbed her insights, repackaged them in mathematical language and academic terminology, and published them as if the discoveries had emerged from laboratory research rather than a night shift welder's practical observation. For decades, welding textbooks taught stress relief sequencing without mentioning the woman who first recognized its necessity while watching hull plates warp under her torch. Yet her legacy permeates modern engineering in ways that reach far beyond shipbuilding. Every welded structure standing today carries her contribution. Every pipeline crossing frozen terrain, every pressure vessel containing dangerous forces, every bridge spanning rivers, all of them incorporate sequenced welds and stress-relieved joints. Silent testimony to the welder who asked why ships were breaking and refused to accept "that's how it's done" as an answer. The Liberty ships themselves are mostly gone now, scrapped decades ago or resting on ocean floors. Of the 2,710 vessels built, only 3 survive as museum ships. The SS John W. Brown in Baltimore, the SS Jeremiah O'Brien in San Francisco, the SS Arthur M. Huddle, preserved but not operational. These floating museums tell visitors about wartime production, about Rosie the Riveter and women in industry, about American manufacturing prowess. But the deeper story is harder to see. It is in the welding sequences that every modern shipyard uses, in the inspection protocols that check not just weld quality, but fabrication sequence, in the engineering courses that teach students to listen to workers who observe problems firsthand, in the manufacturing philosophies that value frontline insight as much as executive direction. The revolution Kaiser brought to American industry was never really about ships. It was about questioning authority, about valuing practical observation over theoretical purity, about recognizing that speed means nothing if quality fails, about having the courage to admit mistakes and correct course, even when correction is expensive and embarrassing. Those lessons remain relevant wherever industries face challenges that conventional wisdom claims impossible. The Liberty ship story proves that the greatest innovations often come from those unconstrained by tradition, that progress requires questioning accepted limits, that human potential exceeds conventional expectations when properly organized and challenged. Kaiser's workers were not superior humans. They were ordinary people achieving extraordinary results because someone believed they could and organized systems that allowed them to prove it. Bessie Hamill was not a genius engineer. She was an observant worker who recognized a pattern and had the courage to speak up despite her lack of credentials. That is Henry Kaiser's and Bessie Hamel's enduring legacy, carved not in steel, but in transformed understanding of what dedicated people can accomplish when freed from the constraints of tradition and challenged to attempt what experts claim cannot be done. From December 1940, when Kaiser signed his first contract knowing nothing about shipbuilding, to November 1942, when the Robert E. Peary launched after less than 5 days of construction, to November 1943, when Bessie Hamel identified the welding sequence problem that was breaking ships, to September 1945, when the last Liberty ship was delivered, the program proved that industrial revolutions happen not through incremental improvements, but through fundamental reimagining of what is possible. The 2,710 Liberty ships built between 1941 and 1945 carried more than cargo across oceans. They carried proof that welding could work if done correctly, that women could do men's work equally well, that frontline workers could solve problems engineers missed, that speed and quality were not opposing goals but complementary ones if properly balanced, that industrial capacity was not fixed but could be created rapidly when necessity demanded it. Most importantly, they carried proof that human ingenuity, when unshackled from tradition and empowered by necessity, can accomplish the seemingly impossible, that one civilian's band idea, executed by thousands of untrained workers, refined by a night shift welder's observation, could change not just a war, but an entire century of industrial practice. The mathematics of warfare are often decided not on battlefields, but in factories. The courage to question convention, the humility to learn from mistakes, the wisdom to listen to those doing the work, these determined outcomes as surely as tactics and weapons. Kaiser and his workers proved that the impossible simply means nobody has figured out how yet. And sometimes, the person who figures it out is the last person the experts expected. Watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.